Welcome to lecture 3.7. So this is one of the very last things that I have to show you about taking the derivative. It's called implicit differentiation, and it's related to the equations of circles, and then we'll eventually use it to better understand inverse functions and their derivatives. Let's get started with some terms. So sometimes it's useful to talk about a curve that isn't technically a function. In other words, in your head you should be thinking something that doesn't pass the vertical line test. But these curves and shapes can be useful, and oftentimes we can still write an equation for them. Even though it's not a function equation, it's an equation, and if we plug in the x and the y's from the points on that shape, those x and y values will satisfy the equation. Usually when we write an equation like that, x and y are both going to appear as variables, but y may not be isolated. In fact, sometimes it's not even possible to get y by itself. There's an example down here at the bottom if you want to see what I'm talking about. In this case, we have an equation where x and y are variables, h and k and r are going to stand for numbers, and y is not isolated. Now, that's not the reason this isn't a function. The reason this isn't a function is because technically this equation is a formula for all of the points on the black line right here. And as you can see, it forms the shape of a circle. So circles, ellipses, foliums, and hyperbola are four most common kinds of shapes that we might want to talk about using implicit equations. You do not need to memorize these three terms. You do need to memorize what the equation of a circle looks like. I'm not sure if you saw that in pre-cal or not, but this is the equation of a circle. H and k represent the center of the circle, r represents the radius, and then x and y are just your variables. So look at this for a second, and can you remind me again, how come these are not functions? Exactly, they all fail the vertical line test. All of them have points that have the same y value and different x values. So if they're not functions, why do we talk about them? Well, they're all equations for shapes. And a lot of times in the world, a mathematician's job is to analyze something about a shape. We'll talk about an ellipse example in class, but interestingly enough, the hyperbola shape right here is related to radio waves and how they're transmitted. Circles are useful for a whole host of reasons, and you can imagine why. And the folium, well, I think it's just pretty, but could be useful as well. Since these shapes are useful, and since we can write equations for them, it makes sense to kind of ask, well, what about their derivatives? What about their tangent lines? So since we have the shape, in fact, let's look at equation A right here. Can you imagine what equation A is going to look like? Exactly, it's a circle, and you recognize that telltale x squared plus y squared equals a number. And it's a circle with radius 5. It looks just like this. So again, my question is, what would it mean to write a tangent line for this equation? Well, a tangent line means the same thing it always means. Here, I'll add a point, and that's a point on the circle. And then a tangent line would be a line that goes through this point and has the same slope as the curve at that point. Another way to put it would be it's a straight line that grazes the curve at exactly one point without crossing any other points. And it makes perfect sense to talk about a tangent line, even though this is not a function. The tangent line just simply talks about the shape of the circle. And as we move around, the tangent line changes. It has a different slope at different points. Equation B is a folium. I just wanted to show you kind of what this looks like. It's not that one. It's an interesting shape that looks something like this. It's kind of a loop-de-loop. Of course, that's not a function. In fact, there are 3 points right here. Definitely fails the line test. But just like with the circle, I can add a point, and it's pretty easy to draw a line that traces the shape of the curve. So in today's video, we're going to be talking about how do we find the slope of that line. In other words, how do we take the derivative of an implicitly defined equation? Let's look at some examples. Before we get started, can you just remind me again what an implicit equation is? In fact, why is this considered an implicit equation? Exactly. So just keeping your mind fresh from the beginning of the video, this is an implicit equation because y has not been isolated. It has variables x and y, but y is not by itself. And actually, it's not even a function, it's just an equation. Because if we graph this, this is actually the folium we were just looking at, and it fails the vertical line test. So we're about to find an equation for y prime. And this is kind of tricky because technically in this case, y prime may not actually be a function. This is not a function. Why should its derivative be a function? I don't know, not necessarily so. But we can find an equation for it, and it's going to be an equation that somehow allows us to identify the slope of this curve at various points. One of the biggest differences with implicit differentiation and all of the other strategies we've learned so far is that when you get your answer for the derivative, it will not necessarily be a function, and it most likely will have x and y as variables instead of just an x. Let's take a look. The strategy is going to be to take the derivative of both sides of your original equation, and when you take the derivative, you're going to treat y as a function of x, not just as a variable, which means we're going to have to use the chain rule, and then in the end, we'll get y prime by itself, and that's just going to be your answer. For a, we have this folium, and my first step is to take the derivative of both sides. By the constant rule, the derivative of 0 is just 0. That's the easy part. By the sum and difference rule, the derivative of this entire function is the same thing as the derivative of each term added together. The derivative of x cubed is pretty easy. That's just 3x squared, because x is just your normal variable. Now, the derivative of y cubed is actually not so simple. You're probably tempted to write 3y squared. And you're not entirely wrong, because that's the first part of it. But remember what we said for step 2? We said we were going to treat y as a function of x. And that means that technically what we've got going on here is a function inside of a function. Y is being cubed, and that's the outside function. And the derivative of the outside function is 3y squared. The inside function is y itself. And we don't have an equation for y, so it's a little bit hard to see that that's a function. But you have to trust that it is. And we're going to, if we treat that as a function of the variable x, it would have a derivative. And what we would have to do is we would have to multiply the derivative of the outside function times the derivative of the inside function. And in this case, the derivative of y is y prime, which really just means the derivative of y because we don't technically know what it is. Notice the difference between the first term and the second term. Can you explain why the process for the second term was a little different? Exactly, because in the second term, y is a function, whereas in the first term, x is just a variable, so we just use the normal power rule. How about in the last one? Are we going to have to use a chain rule here? Yeah, absolutely. In fact, not just a chain rule, but also a product rule, because we're multiplying 9x times y. So I've got the first two terms added together, and then I'm going to subtract the derivative of 9xy. So if I think about this as a product rule, I'm going to think about it as 9x times y. And the product rule says u dv, so u is 9x, times dv, the derivative of y is y prime, and that's dv, plus v du. In this case, v is just the y, and du is the derivative of 9x, which is 9. And I'm squeezing it in here, but you can see what it should be. And then don't forget your equals 0 on the other side. Now, my next step is going to be to distribute the negative, and then I'm going to do combining like terms if I can find any. As it turns out, there are no like terms. Remember, when you have multiple variables in an expression, these multiple variables form their own sorts of like terms. So just because both of these two terms have x's doesn't make them like terms. Or just because both of these terms have y primes doesn't make them like terms, because they also have other variables. The other common source of confusion that I've seen here that I want to emphasize early on is that don't accidentally think that this is y to the first power. It's not. This is y squared. this is y prime. In fact, if it would help you, you can kind of draw them more like commas so that you remember this is a derivative. It's a different variable than y. Of course, it's also a different variable than y squared, but it's entirely different. You can't combine them. Don't try to add the exponents or anything like that. Okay, so where are we in this process? We've taken the derivative of both sides. We applied the chain rule. The last thing we need to do is isolate y prime, because remember, that's what we're looking for. And in fact, the second you get y prime by itself, you're all ready to go. So I've highlighted the y primes in blue here. In order to get them completely by themselves, we'll start by keeping any term with y prime on the left side of the equation, and we'll move any other term to the right side of the equation. Once we've done that, we're going to take out a strategic GCF, and the GCF we're going to take out is just the y prime. Since both of these terms have a y prime, I can write this left-hand side equation as y prime times something in parentheses. And you should be able to check that I took out the GCF correctly by distributing y prime back in. If we multiply this in, do we get the last step? Yeah, sure enough. Okay, amazing news. We're actually right about there. To get y prime by itself now, I have y prime times something equals something else. All I need to do is divide this whole expression, which will cancel it out on this side and leave y prime by itself. And just like that, we're done. We've got y prime isolated. Y prime doesn't appear anywhere over here. And notice what I had mentioned at the beginning, which is that our answer is different than normal derivatives because our answer has variables y and x. And usually that's going to be a hint to you this is not technically a real function. But this equation will allow you to find the slope of our original equation at any given point that's on that equation. Let's try a couple more like this, and then we'll do some examples where we're actually seeing the slope, because that's really when this becomes useful. Let's look at B. Just like before, my first step is to take the derivative of both sides. The derivative of 2y is 2 times the derivative of y. And it would be tempting probably to just say that it's 2, but that would be to forget that y is a function. Anytime you have a y, you're going to need a y prime tacked on to the end of the derivative because we're treating y as a function of x. On the other side, the derivative of x squared is just 2x, and that's just a normal 2x because x is not a function, it's just a variable. And then the derivative of sine of y is cosine of y times y prime, and that's that chain rule. Okay, what's the next step? Exactly. We need to get y prime together on one side of the equation. So I'm just going to subtract cosine over. Now what? Yes, GCF, take out the y prime. And remind me again, how could I check that I did that correctly? Yeah, you can always distribute it back in, check that you got the last step. And then the last step is a piece of cake. Just divide both sides by this term in parentheses. And just like that, we got an answer. And if you wanted to talk about this answer, just remember that this is an equation for y prime. It's not technically a derivative function because this wasn't necessarily a function. If you have a computer, it might be fun to look at Desmos, see what this equation looks like. It's kind of funky. All right, you have a job. 2 for you to do. Same thing, find an equation for y prime. When you press play, I'll show you the answers. Here's number 1. And pause to make sure you have all the steps. And here is number 2. So number two is a little bit messy, so let me run through the steps. We start by taking the derivative of both sides. On this side, that just means taking a power rule, but on this side, we have to use quotient rule. My u and v are clearly defined. I have v squared on the bottom, and then I just used green to show you the derivatives. So this is v du, so the derivative of x minus y is just 1 minus y prime, because x is a variable, but y is a function. Same thing over here. From there, I chose to multiply the denominator over to the other side just to get rid of the messiness, and that canceled it on this side but moved it over here. And then I foiled both of the tops, and I was careful with my negatives. I had some terms cancel, And then from there, I'm just trying to get y prime by itself. So I moved this whole term to the left and that term to the right. And that allowed me to isolate y prime by dividing, which gave me a final answer that's actually surprisingly simple.